PowerPoint presentations that were done as part of workshops in the conservation applications of LiDAR data. These conservation applications were funded by the Environment Natural Resource Trust Fund, the university, the Minnesota Water Resources Conference, the Minnesota Board of Water Soil Resources, the NRCS, and the Minnesota Department of Natural Resources. There were 6 training modules that were created, and this basics training module was produced by Joel Nelson to provide the foundations for the other training modules. So in this exercise, we want to help you understand a few key concepts like what is raster, what are some of the raster operations, what's a DEM, so that we can move on to the more detailed information on terrain analysis, on hydrological applications, engineering, wetland mapping, and forest ecological applications. So this is a basics in the structure that underlies the LiDAR data. The basic structure that you need to understand first and foremost is raster and the concepts of raster data. And raster is used a little less today than vector data. Most people are familiar with vector files, which would be simple files that show the streets and roads, their lines, points, lines, polygons. The raster you probably use quite a bit, but it's within a photo or within a satellite. And it's a series of checkerboards which represent a continuous surface. But it's an idea that isn't as well understood. It's a regular pattern of cells, typically square, and what's in the cell is some information that tells you what that object is being represented. So in the particular cell, we're representing the stream here by turning on the cell. Instead of drawing a line, we turn on a series of cells to represent the stream, or turn on a group of them to represent a lake, or turn on a group of them to represent a real world. And this is very much the same concept that your television does. In order to show a football player, it turns on the pixels to show their face, or to show the football, or to show some person's hand by turning on pixels or dots. It provides that structure. The key for raster is cell size. It's all about cell size. Now, the raster is the original data structure of GIS. So when GIS was first started to be developed in computers, its first data structure was a raster. A series coming from matrix calculations, where there was a continuous surface of on-off cells, and that these cells are quite simple in the basic structure, but grouping them together turns into a little bit of a complex concept for most people. The important thing to remember is that it's cells, it's like a checkerboard, and it's good for continuous data like elevation, and that's what the guts of LiDAR is all about, is elevation. Now, the disadvantage or some of the issues about LiDAR is the cell size. So one of the good things is cell size, one of the bad things is cell size. And the issue of cell size is that you can have little tiny cells that have huge storage cost and processing issues, or you could have huge cells that have lots of things clumped together so that you can't differentiate whether it's a tree or a driveway or some grass because it's all lumped together. The basic data analysis in raster is at its core very simple, but it can get complex conceptually. When you're working with a checkerboard and you're putting that checkerboard together with another checkerboard, you have to deal with all the cells. You can't just pick and choose what you want. When you're putting them together, you have to account for every single cell in the output. So we use the terms map algebra for this special math that we use to process rasters, and we have concepts like moving windows, which we'll talk about. So the term you want to remember is raster analysis. It's all about cell size, and everything is handled as a complete surface. You have the entire checkerboard at all times, and it's brought together with map algebra. And an old-fashioned term in older ArcGIS that's still used is this term raster calculator. It's a special type of math. And there are some examples of this where you're looking at time series, where you're comparing one year to another year by subtracting the cells to say how has this particular cell changed from year to year. Now, how this analysis happens in raster that isn't a simple adding together or multiplying one raster, one checkerboard by the other checkerboard, is that we use a concept of moving window. So there's this window, if you will, that sweeps across the entire raster surface, starting from the upper left, sweeping to the right, and then sweeping back and forth, this moving window. And as that moving window moves across, it performs operations. It can group them, it can take the average, take the mean, so on. And this is used for calculating the slope or hillshade, doing a series of calculations that are derived from this basic raster structure. So the things you want to take away from this is raster. What is a raster? It's the fundamental structure that we start with in LiDAR analysis. And an old-fashioned term for that is grid. And you want to understand that the raster or grid synonyms, and that the grid structure is very, very important, and it's all about cell size. Now we have to deal with the concepts of aligning the checkerboards to make sure they line up, and the tasks we go through to make them line up, which would be resampling. The first, talking about file structure. Now these checkerboards or grids, rasters, are not single files. They're clusters of files that all have a separate purpose. And they're used, you move them around with our catalog, and they're grouped together in E00 or IMG files. And these groupings are very similar to zip files, where you're taking a cluster of files and putting them together so you could transport them. But all the pieces have to exist. It's like a person. You have to have the head and the arms and the legs and the body to have it be a functioning unit. You can't just send the hand or the head. The other problem with grids when you're putting these checkerboards together is that they don't line up. So there are processes to go through the lining up that, if they're the same cell size, that you can snap them, snap the corners so that they can line up. Now that's assuming they're the same cell size. Now the problem is, if the cell size isn't the same, you have to go through some process, some map algebra process, some raster calculator process that you would go through to move from a very detailed checkerboard to a coarse one, or from a coarse one to a detailed one. And that's referred to as resampling, moving from one to the other. Now, when you're doing this resampling, you could be aggregating or subdividing. And as you're moving from one to another, you're changing the size of the database very significantly. So you want to be aware of this aggregation process as it affects your file size. And sometimes there isn't an easy way to go through this process when you're resampling. So there has to be some other statistical process, some types of interpolation. When the grids can't be evenly divided. We can't take one cell and divide it in 4s or divide it in 8s. You need to divide it in some other number. Now, the implementation that we need to understand thoroughly for the later workshops is digital elevation model, DEM, digital elevation model. It stores, it's a raster, and it's a special raster that just stores elevation. So in each cell it says how high it is above sea level and the location of that cell. Now these were prepared originally from ground surveys, and these ground surveys fed topographical maps and contours. And as we moved through the 19th century, they employed stereophotography to create them. And now later in the 20th century, or 21st century, we're using LiDAR to derive these. So there's sort of a time frame of evolution through these processes. Now the stereo pairs are a fairly simple concept. It's very much like the 3D ViewMaster you remember with Mickey Mouse. Is that we're taking a picture from two different perspectives and of the same area, and that we're using the concept of parallax to see the 3D view. And from that 3D view, we're able to measure elevation. It's a very common way for us to do elevation surveys. Now, originally, the elevation surveys, though, were done from land surveys that were created into contours. And these contours in the early 20th century were put onto topographical maps. And these topographical maps were used, they were the workhorse of analysis for many, many years. When the digital revolution came along, we scanned in these topographical maps and took off the contours and used the contours to create this digital elevation model. And so you want to understand its origins. But the reason for contours is that they're an easy way to represent a digital elevation model. It's hard to see a checkerboard of elevation, but it's quite easy to see a contour, which is a line of equal elevation. Now, the surveys that were done to create these today are using total stations or GPS, and they're really quite labor intensive, but they're very, very precise. And we're using angles as well as the GPS satellites to understand where we are and then how high we are above some reference surface. The one that we most commonly use would be mean sea level, or the ellipsoid, but height above ellipsoid, but there are other reference surfaces we're using to measure the height. Now, these models of the topographical features, the elevation in this case, have several different structures. The one we care the most about is DEM. But you want to remember that a lot of times the early data was stored as contours, which are vectors, and that the contour is still an easy way of representing it for people to visualize the change in elevation in landscape. There's a third kind that we're not going to deal much with, and that's a triangulated irregular network, a TIN. It's a surface that's used, that's a combination. It represents the continuous surface of a digital elevation model in a series of vector triangles. And it's used oftentimes in 3D animation because it's very quick to render that three-dimensional surface. Our main concern is the digital elevation model. Now, the DEM, that's what we care about. It's this grid that represents the Earth's surface. It's georeference. It has a location, so every cell has a particular location on the Earth, and in the center of that cell, it has how high it is, or the elevation. And it's just like a raster. It's a series of pixels or cells, and each cell has one value in it, and that's an average of the elevation within that grid. So if it's a 1 meter cell size, it's the average of the elevation within that 1 meter. Now, this is a 3D representation of it. This is a derived surface from a DEM, but you can see that the DEM really helps us understand the landscape very thoroughly by coloring the red high areas, showing the relief with the shadows, the low river valley, or the flatter areas. Now, the key to DEM, just like in general raster, it's all about cell size. If it's a coarse resolution, you're going to have a very rough approximation of the surface. If it's a fine one, you're going to have huge files, but you're going to have a very detailed resolution. Now, from this sort of process, this basic DEM structure, we often do interpolation. Say you want to know the elevation between two cells. What do? Well, you have to use an interpolation process. You have to estimate that value from your two known values. Now, cell size. Cell size is what it's all about. If it's coarse resolution, and that would be I'm showing the true landscape here. The yellow is the true landscape. And if we've got coarse resolution, you can see that coarse resolution, depending on where it picked up on the landscape, would not represent the land very carefully. But a very fine resolution, you can see with more dots, with more cells, if you will, you're able to pick up more of the detail. Okay, why so much comparison why so much interest in LiDAR? Well, LiDAR gives us a lot more information about elevation. As the laser flies over, we're able to get a horizontal resolution of about 1 meter, okay? But our vertical measurements are actually down around 15 centimeters, so that we're able to get very detailed measurements of the elevation, of how high it is above the reference surface, within very, very small areas. So we could have a very detailed representation of the landscape that we weren't able to do before from the stereo pairs or from the ground surveys. The problem with this higher resolution is that it takes a lot more time. It's all about big data and the processing time and the issues of dealing with huge files. The coarse resolution gives us simple answers quickly, but it has, there are trade-offs between the higher and the low resolution. And these are some examples. The left is the fairly common 30-meter DEM we used for many years. On the right is a 3-meter. You can see a little more detail. When you're looking at it, the dark area would be a lower area, the lighter area would be higher, but you get an idea that it's hard to visualize the raw DEM, but you can tell that they're higher resolution with 3-meter. When we're representing this on with some sort of hillshade, you can get an idea that the 30-meter doesn't give you as much information as the more detailed. The problem with the more detailed is that there's way more information. There's 1.5 million points per square mile. So it's huge. More information, more size. And you get an idea here. Here's another representation. Now, this is a derived surface. We were showing before the raw DEM. Now we're showing the hillshade. We're showing a representation of that surface. Oops. A representation of that surface. The representation of the surface with a hillshade. And you can see there's a lot more detail as you move from 10 meters to roughly 3 meters. Now this is a 30-meter. The next one is a 3-meter. So you're moving from 30 to 3. From 30, you see the coarse resolution. You barely see that there's a river here. When we move to 3, you see, well, there's really some sort of drainage here, and there's a large river here, and you're getting a lot more detail. But with this larger detail, you're getting much larger file size. And this is showing the hillshade. Here's a drainage within this landscape, and you can see the drainage very clearly. On the 30, you can barely make it out. Now, contours. What's a contour? Line of equal elevation. So as we move along this line, it's all at 900. So we move along the next one, it's all at 910. The next one is 920, so on and so forth. As we represent this elevation in a 10-foot contour or 2-foot contour, you can see there's just more lines. Now, more lines means more data, but more lines means more information so that you could actually see this drainage, this conveyance within the landscape and the very subtleties of the landscape a lot more easily. This is the end of this lecture.